everybody. So the afternoon talk is by Professor Antonietta Mira from Lugano, Switzerland, who's going to talk to us about zero-variance MCMC. Thank you very much.
Well, thank you for having me here. I'm very much enjoying this day at the Isaac Newton Institute. So this is a joint work with two PhD students of mine, and Mark, who's in the audience, and a postdoc of Mark. So let me start setting up some notation. So interest is in evaluating the expected value of some function f with respect to distribution pi that we might know up to a normalizing constant. If we could generate II draws from pi, then our Monte Carlo estimator would be the average of f along the draws. And we all know that the variance of the Monte Carlo estimator is sigma squared f, which is the variance of f under pi, divided by n, the number of IID draws. Suppose we can now get IID samples, and we run instead a Markov chain that has pi as its unique stationary and invariant and limiting distribution. Well, in which case our estimator would be exactly the same, except that we average f along the path realized by the Markov chain. Our estimator will be asymptotically unbiased, and the variance of the MCMC estimator will be the variance of the Monte Carlo estimator, and we should then take into account that the draws are not independent, so we have the integrated autocorrelation time. And again, we have conditions for a central limit theorem of the MCMC estimator that require conditions both on the chain, either geometrically or uniformly ergodic, and finite second moments or higher order moments, depending on how well behaved is your Markov chain. So this is all well known and standard. And another standard way of reducing the variance of your Monte Carlo estimator is by control variates. So what is a control variate? Well, Z is a control variate if it has zero or known mean under the target distribution, and if it's correlated with the original f that we're interested in estimating. Now, by exploiting the fact that the correlation is non-zero, we can build a new function, let's call it f tilde, which is the original f plus a linear combination or of this control variate. We can have more than one. And simple computations show us that since z has zero mean, the mean of f and the mean of the new f tilde are the same. So rather than averaging the original f along our Monte Carlo simulation, we could average f tilde. And as a result, the variance of the estimator will be the variance of the original f plus the variance of z, of course multiplied by the coefficient a squared, plus 2 times a times the covariance between f and z. So it turns out that we can also derive the optimal a coefficients, optimal in the sense of minimizing the variance of f tilde. And the optimal choice of the coefficients are minus the covariance between f and z divided by the variance of z. Remember, z is our control variable. And as a result, the variance of f tilde will be the variance of the original f multiplied by 1 minus the covariance squared. So the higher is the covariance or the correlation between the original f and the control variate, the higher is the variance reduction. Okay, so this is sort of well known and standard. What I will try to tell you about today is how to design control variates and how to use them in an MCMC setting. The idea comes from the physics literature, but everything boils down to the fact that it is well known that under regularity condition, the score function is zero mean, and therefore we could use the score function as our control variate. Okay, so this is the intuition behind the idea, but let me tell you how we got to this idea. Well, the original paper that inspired us was a paper by Ashraf and Kafarel, published in the Physical Review Letters. Not an easy paper to read, but once you get through it, you get some interesting ideas. So they proposed an interesting way to design control variates, mostly for Monte Carlo simulation. We took their idea, translated it for MCMC simulation, verified carefully conditions for unbiasedness and for central limit theorem, and we experimented with this idea on a bunch of examples. So here's their idea. There are two main ingredients for zero variance principle. By the way, the name zero variance was picked by them. It's a very catchy and appealing name, and I will tell you where it comes from. So the ingredients for zero variance are two. One is H, an Hamiltonian operator that has to satisfy the following condition. And the second one is phi, a trial function that can be very, very general. So given this condition, we can construct an f tilde by taking the original f plus this bit that will represent our control variate, which is taken to be the integral of the operator applied to phi, the trial function, divided by the square root of the target. Remember here, the target is only known up to a normalizing constant, and this goes through also in the setting by Ashraf and Kafarel. Now, under mild conditions, it's easy to verify that the expected value of the original f and of the new f tilde that we've built are the same, mostly because this epsilon bit has zero mean thanks to this condition. As zero mean, of course, under the target. Oops. Yeah, let me see if this trick works. Not sure why it appears. Okay. So the mean of f tilde is equal to the mean of f. By carefully choosing h and phi, we can construct an f tilde so that the variance of f tilde is much smaller than the variance of f, the original f that we have. So, as a matter of fact, we can come up with a choice for the operator h and the trial function phi that actually lead to zero variance. That requires, though, solving this integral equation, which is not easy to do, especially because there's a mu f, which is what we do not know to start with, that appears in this equation. So finding h and phi, solving this equation that guarantees zero variance is not easy. So this is what we have decided to do. We select an operator h that verifies that condition, and in the paper, Ashraf and Kafarel give us at least two choices for those operators. We then specify a family of trial function phi, and we index this trial function by a vector of parameters. And then we find the expression for those optimal parameters in the trial function phi that minimize the variance of f tilde. Then we will see that those optimal parameters are not readily available. We have an expression for them, but they are related to integrations with respect to pi, which is something that we cannot do. So we estimate these optimal parameters through an MCMC simulation, possibly a short independent run. And then we run a new simulation and estimate along the path of the realized chain mu f by averaging the new function f tilde. Okay, so this is what we're going to do. Here are a choice of operators proposed in the original paper. The first one is a Schrödinger type Hamiltonian operator. And the second one has this form, where P is the kernel of your Markov chain. It turns out that this is the operator that is used in a Royal Statistical Society paper by De La Portas and co-authors, well, they don't actually say that are using this operator, but they have a control variate technique that results to be a special case of this general setting by Asraf and Caffarel. So, because they've used this operator already, we've decided to focus on this other operator. So from now on, we will work with this Schrödinger type Hamiltonian operator, and we will take our trial function to be a polynomial times the square root of our target. And depending on the degree of this polynomial, we will talk about first order zero variance, second order zero variance, and so on. So from now on, this will be our operator, and this will be our trial function. We worked out careful conditions that guarantee that with this choice of h and phi, we have an unbiased estimator. So conditions that guarantees that the mean of f tilde is equal to the mean of f. And these conditions are fairly easy to state and verify. In the unidimensional case, you have to look at what happens at the boundary of the supports, and similarly for the d-dimensional case. So you want your target times the derivative of the polynomial that appears in the trial function to vanish at the boundary of your support. These conditions are fairly easy to verify in at least the problems that we've looked at. Okay, so using this h and this trial function, what does f tilde looks like? Well, f tilde is the original f plus, minus 1/2 the second order derivative of the polynomial. This is maybe not standard notation, but it's the notation used in the physics literature. Plus the gradient of the polynomial times the control variate, where the control variate turns out to be minus 1/2 the derivative of the log target. So you see that this is our control variate. So at the end of the day, applying this machinery, very general construction from the physics, we end up using as a control variate something that we all know as zero mean under the target, under, of course, regularity conditions. So if we now take a linear trial function, then the f tilde will be the original f plus A transpose Z. And we can also work out what are the analytical optimal coefficients A. It turns out, mimicking the computation that is done in the Monte Carlo setting that I showed at the very beginning, that the optimal A is minus the inverse of the covariance of the control variates. Okay, since the control variates by construction has zero mean, the covariance is just the second moment. Sorry, the variance of Z is the second moment. So is the inverse of the variance covariance matrix of the control variates times the covariance between Z and F, which is the mixed moment, because again Z has zero mean by construction. Now you see that the optimal coefficients are expressed in terms of averages with respect to the target. So those quantities are not computable, but of course we can estimate them through the path of our MCMC simulation. And you can either decide to run an independent Markov chain to estimate the coefficients, and then run another Markov chain and use the coefficients that you got, but you can save time and do everything on a single simulation. Things do not change. Okay, so questions? Yes?
So the score function has expectation 0 at the true value of theta, right? But not at other values?
No, it has, in general,
Every value of theta?
expectation 0.
Well, with respect to pi.
Yes, with respect to
Not
target.
Oh,
Right.
okay.
So here, everything is in terms of a target pi. Then we'll put everything into the Bayesian setting. Right now, pi of x is our target. That will become our posterior. Okay, so for quadratic trial function, the same reasoning goes through with a little bit heavier notation. But so this is a quadratic polynomial. So we have A transpose and then X transpose BX. And the F tilde is the original F plus a quantity that has zero mean, and we can rearrange the terms in this quantity so that we have the same notation as for the linear polynomial. So we'll have a G transpose Y, where here is a description of what is G and what is Y. Maybe the important thing is to focus on what is Y. So in the quadratic case, Y is a vector containing the Z that I told you before, the derivative of the log target, and then there's a U, which is Z Adamar product with the original X, the original variables, minus 1/2 times the vector ones. Okay, so you have the Z, the U's, and the V. And the V is another vector whose elements have this structure. So you have X and Z. But everything that you need to compute this quadratic polynomial is again in terms of the derivative of the log target. And the higher is the order of the polynomial that you stick in your trial function, the more control variates you will have. So if you have a polynomial of order 2, and if you let D be the dimension where your target lives, you will have D times D plus 3 divided by 2 control variates. In general, for a polynomial of order P, these are the control variates that you get. And you will see with simulation results that I will show you that the more control variates you add, the higher, in general, is the variance reduction that you achieve. Of course, it will take a little bit more computation to get the optimal coefficients. Yes?
Why do you want to write it like that?
The reason I want to write it like that is because then I can easily find the optimal G by using these formulas, right? So you use exactly these formulas with Z replaced by this Y. That's the reason why we want to write it this way. Thank you. Okay, so it's fairly easy to derive conditions that guarantee a CLT for the zero-variance MCMC estimator, where by zero-variance MCMC estimator, I mean this guy here, the average of F tilde along the path of the Markov chain. This result mimics the results that we already have for CLT for a regular MCMC estimator. So if your chain is geometrically ergodic, you need to have moments of order 2 plus epsilon for positive epsilon to be finite. And on the other hand, if your chain is uniformly ergodic, you get away with having moments of order 2 for your control variates to be finite. For quadratic polynomials, you have similar conditions that are, instead of being in terms of moments of the z, are expressed in terms of moment of z times x. If we look more closely at conditions that guarantee the existence of a CLT for the zero-variance MCMC estimator, we need to prove the existence of the second moment or of the second plus epsilon moment, depending on whether your chain is geometrically or uniformly ergodic. So these conditions, if you have a linear polynomial, amount to verify that the Fisher information matrix with respect to location is finite. Okay, so you can work out that this is a sufficient condition for CLT with 2 or 2 plus epsilon, depending on the quality of your Markov chain. And we went further and we verified this condition for, in particular, an exponential family. So if you have an exponential family, so let's call this quantity the Fisher information with respect to location. If you have an exponential family, well, everything amounts to checking that the derivative of the sufficient statistics is square integral with respect to pi, the target. And we verified these conditions for Gaussian exponential, Boltzmann Laplace, and a bunch of other distribution. Here's a sort of a surprising example. For the gamma density, using the previous results, it's easy to verify that that integral is finite for all beta parameters, scale parameters, and for all alpha different from 2. For alpha equal to 2, surprisingly, we were a little surprised by this result, you get that well, you don't have a finite variance in the central limit theorem, despite the fact that a gamma with alpha equal to 2 can be seen as the sum of two independent exponential densities, both of them having finite Fisher information. Okay, so let's now put everything into a Bayesian setting. So in a Bayesian setting, your target will be the posterior distribution, which we know is proportional to the prior times the likelihood. And in this setting, the control variance, Z, will be a function both of theta and the data. Therefore, we need to verify conditions for CLT of the zero-variance MCMC estimator for the specific data set that you have. And this is a method that we have applied to all the settings where we have been using zero-variance. Basically, you assume that the data set that you have guarantees existence of an MLE. Then you express the integral that you want to be bounded in terms of hyperspherical coordinates. And then you prove that the integrand is finite for any x and any theta over the compass set where you're integrating. And using this technique, we prove that we have a central limit theorem for zero-variance MCMC estimator for Bayesian, logic, probit, Garch, and a variety of other type of models. So let me show you some of the simulation results to give you a feeling of how much variance reduction we can achieve. So we start with a probit model. I don't think I need to tell you how the probit model works. This is the likelihood. We use flat priors on the parameters, but you can use pretty much any prior you want. The Bayesian estimator is the posterior mean. Well, using the Schrödinger type Hamiltonian and a linear trial function, it turns out that f tilde for a generic parameter beta is the original f plus the sum over d of some coefficients that we know how to optimize, and the control variates have this expression where phi is the density and capital phi is the CDF of a Gaussian 0-1 random variable. And in this setting, it's easy to show that existence of MLE implies unbiasedness of the zero-variance estimator and a CLT. So we estimated the probit model on one of the very classical data set, which is the Swiss banknotes data set, being based in Lugano. It sounded like a good example. I think you're probably familiar with this data set. Well, in any case, we have 200 banknotes. 100 of them are genuine, 100 are counterfeit. We have 4 explanatory variables, namely the length of the bill, the width of the left and the right edge, and the bottom margin width, whatever they are. We use this explanatory variable in a probit model and want to estimate the probability that a banknote is fake or not. So we have 4 parameters having 4 explanatory variables, and we run a first stage simulation of 2,000 steps. And on this Markov chain, we estimate the optimal coefficients A, and then we run a second stage of the same length. And on this second stage, we average f tilde to estimate the original quantity mu that we are interested about. Those 2 chains don't need to be 2 different independent chains. You can get away by running a single 2,000 steps chain or longer if you have more computational time, and on the same chain estimate both the coefficients and average f tilde. We run a straightforward Gibbs sampler in the flavor of Albert and Schieb JASA paper, and we compare the performance of the regular MCMC, which is obtained averaging f on the path of the Markov chain with the zero-variance MCMC, which is obtained averaging F tilde. Okay, so for the 4 parameters, beta 1, beta 2, beta 3, and beta 4, this is the straight trace plot over 200 iterations of the original F. Okay, here F is just the identity. So this is beta 1, beta 2, beta 1, beta 2, beta 3, beta 4. And here now in red, you see the trace plot of theta tilde, okay, with the control variance added to it. And you see how much stabilization we get in the path of our Markov chain. And if we want to measure what we see, well, we get a variance reduction ratio. So the variance of the original blue chain compared to the variance of the red chain, the zero variance chain, is of the order of 25/100. And this is using a first degree polynomial in the trial function. Okay, so a single control variable. If we move to second degree polynomial, here you see the plot of the zero variance, theta. And here the variance reduction ratios is of orders of magnitude. If you want better plots, here they are. For the 4 parameters, beta 1, beta 2, beta 3, beta 4, on each plot, we have the box plot of ordinary MCMC. So this is the box plot of beta 1. Then we have the box plot of beta 1 tilde using first order polynomial. And then we have the box plot of beta 2 tilde. And the green is ordinary MCMC of length 10 to the 8. Okay, so this is just to make sure that we're not inducing any bias, which we know because we have checked the conditions, but just to visualize what's going on. Same thing for the logic model. So with the same data set, we just changed the link function. Again, we use flat priors. Same operator and same trial function as before. F tilde is the original F plus a linear combination of control variates, where the control variates now have this expression, which is similar to the one that we had before, except that it's in terms of the link function. And you see that the control variates is both a function of beta and of the data that you have. Again, existence of MLE guarantees that your estimator, the zero variance estimator, is unbiased and you have a CLT. Same data set, ordinary MCMC trace plots, the 4 parameters like before, first degree polynomial in the trial function, second degree polynomial in the trial function. We get a smaller variance reduction, but I still think this is impressive. And again, the box plot like I showed you before. Ordinary, first order zero variance, second order zero variance for the 4 parameters of interest. Okay. Then we tried something a little bit more ambitious, Garch model. So ST is the price of an asset at time t. We compute the daily returns, and then we fit a normal Garch 1-1 model. Okay, standard Garch 1-1 model. So we have 3 parameters of interest, the omega, the alpha, and the beta. Here is the computation to get the control variates. So Zj is the control variate for each one of the parameters, omega, alpha, and beta. And here are, so we use as our data the exchange rates of the Deutsche mark to the British pound over the period 1985-1987, 750 observations. We ran a first MCMC simulation to estimate the optimal trial function, and then a second MCMC simulation where we average our F tilde. And here you have the variance reduction, that is the variance of the regular MCMC estimator. Here we estimated the variance with the so-called, but you can use your method of your favorite method to estimate your variance, divided by the variance of the zero variance estimator. And again, this is the variance reduction for first, second, and third degree polynomials. this is 28,000 times better, 70,000 times better. Here are the trace plots, ordinary MCMC, blue, first degree polynomial. In this case, first degree is not that effective. Still, it works, but second degree and third degree, where we finally stabilize everything without inducing bias. Because here are the box plot. Again, the green is the long, very long ordinary MCMC. Regular, first, second, and third degree for each one of the 3 parameters of the model. Then we tried a heavy tail distribution. The reason we moved to heavy tail distribution is because it turns out that if you have a Gaussian target, you actually get exact zero variance. At first, one of the first examples that I had my PhD student try was, well, try with a Gaussian target and see what happens. So he came back and he said, it was a Gaussian, say, 0, 1. And he came back and he said, well, F tilde is always 0. And I said, no, you must have done something wrong. But then we did a computation, and indeed, for a Gaussian target, you get exact zero variance. So we thought that Gaussianity was a feature of the target that would help the zero variance come to work better. So we tried with a heavy tail distribution. So this is an example from a paper of Petros, 2010. So the data is Gaussian, mean mu, variance v. We take a Cauchy prior on the mean, an inverse gamma for v with parameters 1, 1 and 0, 1 respectively. This is the posterior. We work out the control variates for Z1 and Z2. So we have 2 parameters, the mean and the variance. And this is the variance reduction that we get for first, second, and third degree. Quite big. Okay, here is, if you want, the second part of my presentation is, so far I told you about zero-variance MCMC. So the original idea in the physics literature was mostly applied to Monte Carlo simulation. We took it, we carefully verified conditions for unbiasedness and central limit theorem, adapted it into the MCMC framework. But then we realized that, well, to get the zero variance control variate, you have to compute the derivative of the log target, which is the same ingredient that is used in the Hamiltonian type algorithms. In particular, if you're familiar with the algorithm in the JRSS paper by Mark, you know that, among others, that's one of the ingredients that you need. So with Mark, we thought about combining the 2 methods. So we came up with zero-variance Hamiltonian MCMC, and where we used the derivative of the log target twice. First, to guide your Markov chain towards relevant portion of the state space with a clever proposal distribution in your Metropolis Hastings algorithm. That is a proposal that exploits the geometry of the target and achieves convergence in fewer iterations. And then we use, again, the derivative of the log target to post-process your Markov chain. And that will reduce the variance of the resulting estimators. Notice that zero variance is a post-processing technique. So you can run whatever Markov chain sampler that you want, your favorite sampler, and then you take the realized path and you post-process to achieve variance reduction. And then by combining those 2, the realized path is obtained through differential geometric MCMC methods. So to give you a flavor of the variance reduction that we get when we take a very clever sampler, so you might think that using that information twice might spoil the variance reduction, because if you already have a very effective sampler, post-processing your chain with zero variances might not give you such a huge variance reduction. Well, here is the same, not like this, it is the same, okay, so the first one is the logistic model on the Swiss banknotes. So this is taken from a paper with Mark and Fio. So we have compared here the Metropolis Hastings, the Mala, the simplified Mala, and Mala, Hamiltonian Monte Carlo, and Riemann manifold Hamiltonian Monte Carlo. So we have different samplers, and in magenta here you see the box plot of the regular F. This is the box plot of the first order zero variance, and this is what you will get with second order zero variance. And you see that you get a variance reduction consistently throughout all samplers that you use, and for all 4 parameters. So rows are the 4 parameters, columns are the different samplers, and then you have regular, first order, second order zero variance. Okay, similar plot for the Probit model. Here we change data set. It's not the banknote data set, is a vasoconstriction data where we only have 3 parameters. Again, different samplers, and again the box plot for MCMC, first order, second order. And then here is a Fitsum-Nagumo ordinary differential equation problem, 3 parameters, and again you see the variance reduction. But let me give you some numbers rather than just plots. Okay, so here is the variance. So this is back to the logistic regression model. So regular MCMC, linear zero variance, quadratic zero variance, different samplers, and we have the variance for each one of the parameters, theta 1, theta 2, theta 3, theta 4. This is the banknote data, and this is the variance reduction factor. In boldface, we have highlighted the combination that gives the highest, the smallest variance at the end of the day. And notice that smallest variance does not mean highest variance reduction factor. Because, for example, let's focus on this line. This is Riemann manifold Hamiltonian Monte Carlo. First parameter, this is the variance of the MCMC sampler. This time we estimated the variance through 100 independent runs. This is already very good small variance compared to the other samplers, because this is a very effective way of setting up your Markov chain. Still, we get 1 order of magnitude variance reduction by applying linear zero variance, and even better with quadratic zero variance. And this is stable across all parameters. Similar table for, this is the Probit model for the vasoconstriction data. Okay, here we go. Again, the winner is Mark. But Mark combined with zero variance does even better, with variance reductions, again, of orders of magnitude, and consistently when you move from linear to quadratic, you basically gain at least 1 order of magnitude. And this is the ODE. Okay, on the ODE, M-Mala seems to be the better sampler, at least for theta 1 here. Metropolis Hastings seems to be doing better. But despite the fact that the better sampler varies depending on the problem at hand, what's important to notice is that the variance reduction that you get is consistent of the order of orders of magnitude. And then finally, actually, forget about these tables. The last thing I wanted to tell you is that what is the runtime? What is the extra computational time that we need to compute the F tilde, right? Because you have to spend some time finding the optimal coefficients for your control variance. Well, okay, so here you have simulation time of your Markov chains, and then you have simulation time with zero variance, and for quadratic zero variance, and the additional computational time when we move from regular MCMC to zero-variance MCMC for linear zero variance is less than 0.05% of the original computational time. So you spend very little time computing this control variance. And if you move to quadratic zero variance, well, the extra computational effort depends on setting, but is always less than 0.25%. I think this is the highest that we get, but most of the time is less than 0.1%. So very little additional computational time to get your zero variance or your control variance. Okay, so let's go back to this and conclude. So what I've given you a way of constructing control variance for MCMC simulation that is very well suited for Bayesian inference. We have derived conditions for unbiasedness. We have derived conditions for unbiasedness and CLT of the zero variance MCMC estimators. This is something that was missing in the original paper by the physicist. And then we have tested this idea and verified the conditions for CLT in a variety of models. And as a result, we can conclude, based on our own experience, but I know others are using this technique in different settings, we can conclude that the zero variance strategy can reduce the variance of your original MCMC estimators significantly by orders of magnitude with a relatively small, I would say negligible, additional computational cost. Of course, you have to take the effort of computing the derivative of the log target. Okay? So this is offline computation. And zero variance strategy is very efficiently combined with differential geometry MCMC, because once you've computed those derivatives, you might as well use them twice. Let me add two things on top of this. Mark has a very interesting paper that uses zero variance within the context of estimating the base factor from your MCMC simulation. And it's really, again, the variance reduction that you get is incredible, of the same order of magnitude here. And I'm working on settings where you cannot compute exactly the derivative of the log target, but you have a way of estimating it. In particular, for doubly intractable problems, the derivative of the log posterior involves the normalizing constant of the likelihood, which we do not have, but we have already very encouraging results for the Ising model and the ERGM model that shows that the extra bias that you might induce when the exact derivative of the log likelihood is not available in closed form, but you estimate it, is way more than compensated by the variance reduction that you induce. So even in setting where the derivative of the log likelihood is not, log target, is not available, you can estimate it, and the trade-off little bias that you induce that you can actually control, because the way we estimate, it's under control. The bias bias that we induce is under control, the trade-off between induced bias and variance reduction is still in favor of using the zero variance. Thank you.
Questions?
Can you give a little perspective on where this method is most effective and what problems it's not effective in? So for instance, if you had really high dimensional case, is it hard to use this kind of method? Is it really, it sounds like maybe it's really best suited for the situation where each iteration of the Markov chain is quite expensive, but maybe it's not a high dimensional case.
Okay, so certainly when each iteration of your MCMC simulation is expensive, you definitely want to use this zero variance, because with smaller number of iteration, you will get the same variance of a much longer chain if you were to use the zero variance strategy, right? So if it's costly to do one step in your MCMC, you should definitely use this control variance technique, because you can run a chain that is 100 times or 1,000 times smaller and get the same variance of a much longer chain where you average F rather than F tilde. So definitely use it there. Second, multidimensional setting. Well, it doesn't matter how high dimensional is your target, because typically you want the average of a single parameter. So you're interested in the marginal posterior of each one of the parameters, typically. So you would construct control variance for each one of the parameters in your vector, okay, in the posterior. At least this is the approach that we've always taken, okay? And in particular, you don't have to construct control variance for all the parameters. Since this is a post-processing technique, you might have a nuisance parameter that you don't care about. You don't want to estimate those with small variance. So you can do the effort of doing the zero variance technique only for those parameters that you really care about, okay? Or maybe for those parameters that in your original simulation show a very high variability, because some of the parameters you might be able to estimate well with little variability. Some of the parameters along your original path might vary a lot, and you might try to stabilize only the ones that you really care about or they really need to be stabilized. And then in terms of shape of the target, well, we thought that Gaussianity was one of the key, but apparently, well, it's not, because even with very heavy tail distribution, we still do a good job. Yeah, I think this is everything.
So you mentioned the paper of Petros where he does this sort of control variant.
Yes.
So I mean, did you compare to see? I mean, it's essentially two questions in one. Did you compare to what they did in terms of empirical performance, and what's your? I mean, in a sense, it's a bit.
Their setting is much more complicated,
Uh-huh.
because first of all, it only applies in a Gibbs sampler setting.
Okay.
And it requires to solve, how's it called? It's much more complicated than this. And, well, first of all, the way they design their control variance is unrelated with the setting where I've put everything. So their framework is a special case of this setting, but they didn't realize that, okay? So first of all, like, they don't have linear, quadratic, or higher order polynomials. Basically, they just stop at linear in some sense. And we can go much better than them by having a higher order polynomial, okay? So in terms of variance reduction, no matter what, with this setting, I think you can do better, because you can control the degree of variance reduction by putting extra effort in deriving first, second, or higher order control variance. And moreover, their setting requires to know the transition kernel, like, okay, well, the Hamiltonian, the H, sorry, not the Hamiltonian, the functional H that turns out to be the one that is used to drive the setting requires to be able to write down explicitly the transition kernel. And in some setting you can, for example in a Gibbs you can, but in general you always miss, I mean it's complicated as you know, because you can write the probability of moving away, but then probability of staying where you are, it's a mess, okay? So since you need to write down, since H is expressed in terms of your transition kernel, you can have the transition kernel really available in some setting, but in most settings you don't. So when you don't have that, their method doesn't go through. While with the Hamiltonian operator, it's very general and it's not related to the Markov chain that you're using.
Thank you very much.